Okay, I think everything's in order now. I hope you can all see the slide. So, thank you. So, hello everyone, and welcome to the second international workshop on video retrieval methods and their limits. I'm going to start off by introducing the people who worked on this workshop. My name is Asad, and I'm one of the organizers of this workshop. The other organizers are George, Werner, Keith, Luca, Klaus, and Ian. And the organizers of this workshop are the people who manage Retrieval and Video Browser Showdown. We also had a great program committee that helped us with the paper reviewing as well as other general stuff for the organization of this workshop. So coming to the motivation and objectives of this workshop. Now, we all know that there is a large amount of video available online, whether it's on social media platforms or on other video platforms. And with this increase in video, we also have this increased need of actually understanding what is happening within these videos, whether it is to help us search these videos or to help in accessibility features, etc. And earlier, we were limited in working with videos due to limitations in hardware as well as software. But in the last decade or so, we've seen much larger data sets. Started off with ImageNet and images, but we now have very large data sets in videos as well. And the computing power has increased tremendously, and that has brought us architectures in deep learning that allow us to work on problems that were not possible a few years ago. So video retrieval research has been moving at a rather brisk speed. And the main objective of this workshop was to bring together researchers to discuss the recent video retrieval systems and datasets, but also what challenges we face and what are our current limitations, whether these limitations are due to the data sets, whether they are due to the architectures that we're working on. We can discuss these. Obviously, people will have different viewpoints on these, but it's very interesting discussion. So this workshop calls for contribution in content-based video search. And this video search can be using either natural language queries. So you could have general natural language queries, and you're supposed to retrieve videos that satisfy these queries, whether you can actually localize them within the video. That's an additional bonus at this point. Or you could also have image and video based queries where you could search based on certain images or videos and find similar videos. And when we talk about video retrieval, there can be two types of problems actually. So we have the general video search. We also call it the ad hoc video search in the retrieval community. And this ad hoc or general video search usually has an open world, a real world scenario. So you could have any general query regarding these videos, and you can and you're required to find what is, and basically you're required to search for that query within a general video data set. The second problem is the instance-based search problem, and this one is actually usually a closed world scenario where you're trying to find particular people, perhaps particular objects, and doing some specific actions, etc. So we're interested in both general video search as well as instance-based video search problems. So the organizers made available 3 datasets for this workshop, but these datasets are also available, are open source. We have the V3C1 dataset, the Vimeo Creative Commons dataset. This is about 1,000 hours of video. And this is the general video search dataset. The second general video search dataset that we have is the Internet Archive, IACC.3. This is about 600 hours of video, and it has 90 queries with the ground truth available. And finally, we have a instance-based search dataset. This is the BBC EastEnders soap opera dataset. So it has episodes that span over 5 years, resulting in about 464 hours of video. And you have 177 queries with ground truth available with this dataset. And so this here is the, so you can see the program details for this workshop. We have 3 very interesting invited talks by Professor Chin Jin, Dr. Giuseppe Amato, and Dr. Dima Damon. And we also have 3 oral paper presentations in this half-day workshop. And towards the end, from 12 to 1 p.m. Eastern time, we also have a networking session on Gatherly. So you're all invited there. It would be an informal gathering where we can meet the other participants or the organizers and discuss things which we might not have been able to during this workshop. And we'll start off with an invited talk, but so if you have any questions, please feel free to ask them at the end of the presentation. You can just unmute yourself or raise your hand, either way is fine. Or if you would like, you can also write the questions in the chat box in Zoom. So our first invited speaker is Dr. Chin Jin. The talk is titled Video Retrieval and Description by Natural Language. Dr. Jin is a full professor in the School of Information at Renmin University of China, where she leads the AI M3 lab. She received her PhD degree in 2007 at Carnegie Mellon University. Before joining RUC in 2013, she was a research faculty and a research scientist at Carnegie Mellon University and IBM Research Lab, China. Her research interests are in intelligent multimedia computing and human-computer interaction. Her team's recent works on video understanding and multimodal affective analysis have won various awards in international challenge evaluations, including CVPR ActivityNet Dense Video Captioning Challenge, the NIST FretWid VTT evaluation, the ACM Multimedia AVEC, etc. So Dr. Jin, you have the floor. I'll stop sharing and you can show your screen.
All right. Can you hear me okay?
Yes.
All right. So can I start sharing my screen?
Yes, please.
Okay. Can you see my screen?
Yes.
All right. Okay. Thank you, Asad, for the introduction. And then good morning to the Western audience, and then good evening to the Eastern audience. And then thank you for the invitation. I'm very glad to have this opportunity that to share some our recent works on video understanding, specifically video retrieval and description by natural language. As it also mentioned about with the like personal smart mobile devices and then internet technologies, so we have massive video data recorded and uploaded to the internet every day from our like personal mobile devices or surveillance cameras and so on. So we can have get access to years of video data on sites like YouTube, Vine, Facebook, TikTok, Bilibili, and etc. So it is impossible for us humans to browse through this video data. Therefore, extracting intelligence from video content is of great value. So actually, video understanding has been explored in artificial intelligence and then computer vision research area. And then, so the video understanding, this term is a general term, and then it really covers a very broad area. So we can look at related works from different perspectives. For example, understanding can be at different level, which can be represented as by the different outputs from different understanding systems. For example, the action label from the action classification, and then the relation triplet from the relation detection. And then it can also be a natural language or sentence or sentences or paragraph to describe the detailed content of the video. And then also we can focus on understanding in different domains, including the general domain at the course level or specific domain at the fine-grained level. And then the understanding can also be from different aspects, including the objective aspect and the subjective aspect. For example, what affection can be solicited by the video or the image. To be specific, for example, for the action classification, it is the classic task in computer vision as well. And then, so there have been different data sets to support the research in action classification, including the general, like in general domain, the earlier small data sets like UCF 101 to latest the larger data sets such as ActivityNet, something, YouTube aiming, etc. And then also there have been data sets focusing on specific domains, and including the general like sports domain, and a more fine-grained, fine gym, or like a fine figure skating, and dancing, cooking, and shopping, like specific domain. They more like focus on the fine-grained action recognition. And then the visual relation detection can be considered as a higher level understanding beyond the action classification. And it requires the system not only to detect or identify the action, but also the subject and object of the activity. The output is normally in the triplet format, such as subject, predicate, and object. So comparing to the image visual relation detection, video relation detection is more challenging because it requires the system to track the relation along the temporal dimension as well. And then beyond the relation detection, video description generation or video captioning can be considered as a further higher level of understanding of the video content. And then also multiple like different data sets have been collected to support the research on video captioning. And then researchers have also focused on different aspects, different perspectives for the video captioning. For example, general, like one sentence short video captioning, and to the dense video captioning or paragraph video captioning. And then some works focus on like the novelty captioning or the more diverse discriminative captioning and controllable captioning, informative captioning, etc. So, and then there are also some works focusing on the fine-grained understanding in specific domains, as I mentioned, and also previously, including like in the sports domain, the dancing, cooking, and shopping. So in our lab, we also proposed a data set to support the fine-grained video understanding in the makeup domain. So basically, we collect a large video data sets in the makeup domain, and then we have some detailed annotation about the steps and then the action area and etc. For this video, and to support it, to do the fine-grained video understanding work. We actually we also held a competition evaluation task in last year's SVPR conference. And then beyond all the related tasks that I mentioned in previous slides, more like the objective, from the objective aspect to do the video understanding. There are some also works focusing on the subjective aspect of video understanding. For example, more concerned about the actions or factions related to the video or image. So I just briefly go through from my perspective. What I see, like some research works have been done in the video broad, like video understanding area. So in the following talk, I will mainly focus on present some of our works in the video retrieval by natural language and then video description by natural language. First, video retrieval by natural language. So, this figure here just illustrates the video retrieval by natural language task. Basically, the query is in natural language sentence format instead of a simple like query words or query phrase. And then the task is basically just a video text matching, and given the query sentence, and the system match the candidate video and then output the relevant videos in the ranked order. So the core of this retrieval matching task is how to do the video and the text matching. So one of the dominant approaches is to learn the joint embedding from the two modalities, and then measure the similarity in the joint space. And so, however, this type of approach normally just embedding video and then text natural language sentence into a one video, like one vector. And then this is really very core at the course level, and it will lose a much detailed information from the video and then from the sentence side. So to overcome this limitation, with our baseline model, basically, as shown in this figure, try to do the video and then text encoding at multiple levels. Basically, this figure shows the overall framework of our baseline video text matching model. It contains a video encoder, a text encoder, and a video text matching, like a joint embedding space. So from the video encoder, basically we encode the video information at 3 levels. And at the level 1, we have this basically for each frame we have a CNN embedding, and then for the level 1 we just do the main pooling of the frame level video features. And then at level 2 we apply a bidirectional GRU for the temporal encoding of frame level features. And then at level 3, basically we apply a convolution neural net over the hidden state sequence from the GRU, bidirectional GRU. And basically we wanted to capture some temporal local information. And then similarly at the text side, from the query sentence, we also perform the 3-level embedding. At the level 1, again, is just a main pooling over the word embeddings. And then level 2 is applying a bidirectional GRU to over the hidden state sequence and try to capture the temporal information. And then again, also level 3 will apply a convolution neural net to try to capture some local information. And then with the embedding from both sides, we project them into the joint embedding space, and then we learn the joint embedding, optimize the joint embedding space with the triplet loss. And then, so that's the baseline. So although we try to use multiple levels to encoding the video side and then textual side information, we still like didn't specifically capture the video and then cross modality information at the fine grain level. And then, so we consider that to have the more precise matching between the video and the text, it is very important to understand the fine-grained semantics in the query sentence. And then normally a sentence have this natural hierarchical sentence structure. For example, the whole sentence it describes an event, and then the event naturally involves different actions, and then an action relates to different entities. So it really shows a natural like sentence hierarchical sentence structure. For example, as this graph shows, like the entity and egg is a patient of the action broken. Therefore, so we wanted to like capture this fine-grained local components and then how they compose into a whole sentence to come up with the to describe the event. Such fine-grained information will help us to do more precise and better matching of the video and the text. So and in this work, which we published in last year's CVPR conference, we proposed a hierarchical graph reasoning module, HGR module. So this figure basically shows this module framework. It contains three components: the hierarchical textual encoding, and then the hierarchical video encoding, and the video text matching. So basically, for the text query sentence side, we first decompose the sentence into the semantic row graph, as shown in this figure. The purple, the pink node is the event, the global like event node, and then the green nodes are the action nodes, and then the yellow nodes are the entity nodes. And then we initialize the graph. Basically, we apply a LSTM to get the contextual aware word embedding. And then for the event node, we basically just perform the weighted average of all the word embeddings within the sentence. And then so for the action and the entity node, we just apply the max pooling of the constitutive words within this local structure. And then so in order to capture the interactive context of different nodes within the graph, we then apply attentive relational GCN to encode more contextual information. And then we also factorize the relation matrix in order to avoid the overfitting problem. So at the end, for the query sentence, we will have 3 levels of embeddings, the corresponding to the more global, like event level, action level, and then entity level. And then on the video side, we also wanted to have this multi-level embedding, and as also like video naturally also contains multi-levels aspects involving like the detailed objects and then actions and then also the overall like event. However, it is very challenging, like we parse the video directly, just as what we did in the text, because it will require object detection, tracking, action segmentation, etc. So we then ends up just do the video side hierarchical encoding in a very simple way. So basically, we use different levels of text as a guidance to learn the diverse video representation. Basically, we will apply different weights for from the text side, and then in this way we can come up with the video level, like embedding from different corresponding to event, action, and entity at the different levels. And then with the course modality embedding at the different levels, and then in the video text matching module, we basically do the matching at the different corresponding to different levels. So at the event level, it's like we do the global matching, and we basically apply the cosine similarity. And then for the action and entity level, it's corresponding to the local matching. We apply the weakly supervised attentive alignment, and then compute the similarity. And then so we use contrastive ranking loss as our training objective to optimize the model. And then here we show some experiments on 3 different data sets, including the MSR-VTT, and then TGIF, and then Vertex. So this is in domain, like cross-model retrieval experiments, because we for each data set we train on this data and also test on the same data set. Comparing to the SOTA models at that time, and so basically our HDR model outperforms the compared models, and then achieve the SOTA performance on all 3 data sets. And then here we compare the, we also conducted cross data sets experiments. So basically we train on MSR-VTT and then tested it on YouTube to text. And then comparing to the in-domain, which in the table, above table, that's an in-domain experiments, which means we train on with MSR-VTT, also test on MSR-VTT. As we can see that the SOTA model on the in-domain set under the in-domain setting, so it improves the baseline VSE model, but on the cross data set setting, it cannot carry on the same improvement. However, for our HGR model, we can see the significant improvement over the baseline in either in-domain and cross-domain experiments. So which demonstrate that our HDR model has better generalization ability. And so to summarize the video retrieval by natural language work, so basically our baseline model follows the video text matching dominant approach, like which we try to learn the cross-modality joint space representation. And then in our later work, we propose, we try to decompose the video and text at different levels from global to local. And then in order to perform more fine-grained, more precise text video matching. And then it turns out the proposed model can have better generalization either in domain and cross-domain video retrieval. And then our model and the data are all released on the GitHub. And then if you can check out our paper and then codes if you have any interest in the detailed work. So next, I will present our some of our works on the video description by natural language. Um, video description by natural language is also called video captioning. So the typical, like the standard task is concerning the short video captioning, which is also one of the core tasks in the track weight evaluation. So basically, in this task, we deal with the trimmed videos. These videos are typically in 5 to 20 seconds long, and then there's only a single event in the video. So the target is to generate one sentence to describe the event. However, in the real applications, we often deal with untrimmed videos. They are typically longer videos, like in 5 to 10 minutes long. And then normally there are multiple events. Therefore, only one sentence is not enough to describe the rich content in these untrimmed long videos. Therefore, researchers propose a more challenging video captioning task called dense video captioning, or sometimes also called paragraph video captioning. So basically, this task involves, you have to first detect meaningful events in the video, and then generate with event description. So basically, for the long video, we will have multiple sentences or a paragraph to describe the video content. So I will talk about our works related to video captioning, short video captioning, and dense video captioning. First, for the short video captioning, as I mentioned, NIST track weight video to text VTT evaluation is about short video captioning. So basically, given a short video, we need to generate a natural language sentence to describe the video content. So we participated in this VTT evaluation in consecutive, in 5 years, I think, consecutive 5 years, we participated in this evaluation. So in our, I will first present one of our entry system in, I believe this is our entry system in the 2019 evaluation. So there we basically consider two major challenges. First, we need a good video encoder to represent the comprehensive video semantic. And then we need a good video a caption decoder, which can generate accurate and fluent descriptions of the video. So this is our, this figure shows our like the general like framework of our evaluation system. So basically, it has a video semantic encoding, which involves a multimodal fusion and semantic concept enhanced video description generation, and then a video caption generation, which includes topic guided video caption generation, and a re-ranking strategy, which is enhanced by self-defined relevancy and fluency rewards. So for the video semantic encoding, because video naturally contains multiple modalities to deliver rich semantic information. So therefore, for the encoding, we need to consider both the available modalities, which can help to do the video retrieval. So that means like we also include 2D and 3D visual information and audio information. So in addition to the multimodal fusion, we also consider use concept to reduce the semantic gap between the video representation and mental representation. Basically, we leverage the some pre-trained concept detector, and then to to predict visual concepts based on video features, and use that to further enhance the video encoding. And then for the video caption generation part, this figure shows that video has very diverse topic, and then it shows on the language side, it shows that under different topics, the vocabularies are very different, and then also language style also varies under different topics. Therefore, we propose a generation model with latent topic guidance. So basically, the caption generation can be formulated as a conditional sentence probability, and then we can factorize it over latent topics, and then this, if we parameterize the latent topic distribution, and then parameterize the topic aware sentence distribution, this will lead to the topic prediction network and then topic aware caption generation network. And then basically, this figure shows the overall framework for our latent topic guidance caption generation. So basically, we leverage some pre-trained topic mining, and then we can predict to learn some latent topics, and then we use this latent topics as teacher topic, and then this teacher topic can guide the latent topic learning by introducing topic prediction loss. And then we integrate the topic prediction and then caption generation into a multitask framework. And then we use topic prediction loss and the caption generation loss together, and then to jointly to optimize to learn the to optimize the model structure. And then in addition, we'll also consider the temporal attention mechanism and a semantic attention mechanism. So basically, we wanted to use this attention mechanism to focus on relevant frames and concepts when generating each word. Also, we, in addition to the maximum likelihood optimization strategy, we also incorporated the reinforcement learning strategy to further boost the performance, caption performance. So here we define two reward function for the reinforcement learning. That is the fluency reward function and the relevancy reward function. So basically, the fluency reward function is computed based on a pre-trained language model. We can basically pre-train the language model on the ground truth caption data, and then so basically these fluent sentences will be generated with high complexity, and then therefore we can use this word prediction probability as the fluency reward function. And then for the relevancy reward, we can leverage some pre-trained like video text matching module, and then to reward like the videos which are similar, they should have close distance in the embedding space. So with these two reward functions and then the reinforcement learning optimization strategy, it further boosts our captioning performance. So finally, we can basically apply different models to generate multiple caption candidates, and then so we wanted to ensemble these multiple captions. So how to better ensemble these captions, because maybe different caption models can provide a complementary information. So ensemble really to let us to get the wisdom of the ground. So basically, for the re-ranking, we also consider from multi-aspect. For example, we can leverage previously described the fluency and the relevancy as guidance to re-rank the candidate captions and then to select better captions for the final caption generation. So with all these model components, our evaluation entry in 2019 achieves some very good results in the evaluation task. Okay, so that's all about the short video captioning. So dense video captioning is more challenging because it involves detecting meaningful events in the video first and then generating description for the events. So previously, the dominant approaches for dense video captioning involve two-stage processing. The first step to detect short events, and then generate a caption for the events. So basically, we consider there's the drawback for such a two-stage framework because the first step, event localization or event detection, is already very hard task, and then so poor detection, the errors made in the detection will greatly hinder the final captioning performance. Therefore, we ask the question that is it really necessary to have the two-stage processing? How about we just ignore the event detection stage and then just have one stage where we can directly generate the paragraph from the video, based on the video. However, in order to reach this goal, we consider there are three main challenges. The first is about inefficient attention computation. Because we are dealing with the long video, the whole video will be input to the model. And then for the at each generation step, we need to compute attention weights on all the candidate video frames. So that's very huge attention computation burden to the model. So how can we deal with this attention computation? And the second is about redundant event description. Because with the limited training examples, it is very hard to learn effective attention mechanism with so much attention candidates. Therefore, the model tends to get stuck in few salient frames and then repeatedly just describe these salient frames related events. So we'll describe redundant events. So how can we deal with this issue? And then lastly, on the language side, because for paragraph or dense video captioning, we need to generate long text. And then, so the model tends to fit the ground truth during the training. So the model prefers to repeat high frequency words and phrases. And then in this way, it will generate just some boring language description. So how can we deal with this, and then in order to generate more diverse and captions? So basically this work, this is our CVPR this year work, and so this worker shows our proposed one stage dense video captioning framework. So corresponding to the three challenges I just mentioned, we propose corresponding solutions. So for the inefficient attention computation, we basically propose keyframe-aware video encoder. And then for the redundant event description, we propose a dynamic memory enhanced decoder. And then for the boring language generation, we have the diversity-driven training strategy. So for the keyframe aware video encoder, so because as I just mentioned that during the attention computation, if we need to attend to all the frames in the long video, that will really that's a really huge attention computation. So how about just we can, if we during the video encoding, we can also at the same time select keyframes, the salient frames. So so we can simultaneously encode the video content and then select keyframes. So we introduced the selecting keyframe selecting layer in the encoder. But if we just use the caption loss, like a caption generation loss as a guidance to optimize the keyframe selection, that's not sufficient. So therefore, we consider that the keyframes should also represent the semantic content of the whole video. Therefore, if we use the keyframes, we should be able to reconstruct the visual semantic for the video, and then the whole video the semantic visual semantic from the whole video, and then the semantic from the keyframes should be closed in the visual semantic embedding space. Therefore, we introduce a reconstruction loss here to help the learning of the video encoder, specifically the keyframe selection layer in the video encoder. Also, in order to penalize the encoder to generate more keyframes, we also introduce a sparsity loss to basically penalize the encoder generating too much, too many key video frames. Okay, so for the dynamic memory enhanced decoder, the motivation is that also like at the decoding side, if we for the attention, there's also too much candidates, too many candidates we need to attend to. So basically, instead of attending to the directly attending to the video embedding encoding from the video encoder, we design a video memory. So we just attend to the video memory, and then specifically we introduce two strategies: the progressive memory exposure and over-access the memory decay strategy. For the progressive memory exposure, so the idea is we can gradually add new video frames to the memory record, so that push the model to describe gradually, to move on to describe new content in the video. And the over-access memory decay strategy, so basically it removes highly attended video frames from the video memory. So basically just force the model to avoid, to prevent model to describing redundant video content, and then move on to describe the new event or new content. That's the purpose of this video memory design. And then on the language side, as I mentioned, it is also important for the long paragraph caption. It has from the language side to avoid the boring or the redundancy in the caption text side. So basically, we introduce a diversity-driven training strategy. Here we have some like high-frequency word penalty and a high-frequency phrase penalty. So to penalize the model to repeatedly generate the high-frequency word. Sometimes these high-frequency tokens or phrases they are just with a higher probability. They are errors actually. They are not like relevant to the video content. So with these all three losses combined together, we use them jointly to optimize the model network. Okay, we conduct and then we conduct experiments on two data sets, ActivityNet and Charade's caption data sets. And then we use the accuracy and diversity related evaluation matrix for the performance evaluation. Okay, here this table compares our model to some sort of models. So in the first block, these models they need the ground truth event segmentation. Like they need to the event detection part, like provided event detection. However, our model does not require event detection. We can just directly generate the caption in one step. And then even like for our model, even we do not have a ground truth event proposal, our model still achieves better performance on the accuracy and then diversity. And then also we achieve competitive diversity results comparing to the human level. Okay, this table shows the ablation study. So basically, on the decoder side, the memory decay and then progressive exposure strategies both help to improve the model performance. And then the penalty, like on the language side, the penalty, and then they both bring some gain to the model performance. And then these figures basically shows that with our keyframe selection strategy, we can save time while keeping maintain the caption performance. And then we also tested on different data sets, and then our model generalized well on these data sets as well. And then this figure shows the visualization of the attention. So basically, for the baseline models or other social models, they tends to focus on only a few like keyframes, and then that will generate like redundant, and they will only focus on these keyframe related events. However, our model can have a more healthy like attention pattern, so we can progressively attend to different keyframes in the video. And here I show some case study, and the red shows basically is the high frequency tokens and phrases. Sometimes, however, in our this is our model generated caption, so we can have more like fluent and then diverse, attend to diverse event in the video. And so basically our model can generate more diverse and coherent paragraph compared to other models. Okay, to summarize, I mainly focus on video retrieval by natural language and video description by natural language in this talk. However, video understanding to try to extract intelligence from video is really very valuable and then a hard research topic, because we are in the age of big data, and we we have like massive video data. It needs better and then more intelligent technologies for video analysis, and then track with the tasks and evaluation tasks in the track with benchmark, all related to the general, like a broad area of video understanding. And then it can support, I think it triggers all the researchers to perform some valuable research along this in this area. Okay, so that's all I wanted to share today. Thank you.
Thank you. So we do have a question in the chat. And George is asking, regarding dense video captioning, how long on average are the videos that are in the mainstream datasets?
Okay, so typically the long, I think I have the long video normally in 5 to 10 minutes long.
Okay.
Yeah.
So I had a couple of questions. The first one is, so regarding the affective analysis, where you're trying to find out the emotions, does ethnicity of people play an important role in that? And if so, like, do we even have data sets that represent different ethnicities? Because I'm not sure that everybody represents the emotions in the same way. So I was just wondering.
Right. Yeah. So there's some interesting tasks. I think I remember also in this year's CVPR, there's also a workshop on challenge task. So they have very interesting data sets. So basically, in this data sets, they have some like video media data played, and then some audience watch the video, and then they capture the actions, like reactions from the audience. So basically, that's what I think that's very interesting data sets that can support what I mentioned earlier for the affection and subjective aspect for the video understanding. So basically, what the video can solicit, what actions like the audience will have while watching the video. So I think there are some related works on the a video, like predict a video interestingness, video memorability. For example, how if this video will cause interest for common like the audience, how long the video content is a video content interesting enough that audience can memorize for a long time. And so there have emerged some data sets for this kind of like more affection related research for the video understanding. I think that's also very interesting.
Yeah, thank you. So we have Werner has raised his hand. So Werner, if you could unmute yourself and ask the question.
Yeah, thank you. Yeah, I have a question actually about language-based retrieval. So the queries we have typically in the benchmarks are rather compact, and of course only always cover part of the scene. So in interactive retrieval, we see that the human user that formulates the query sometimes suffers from the ambiguities of how that text could be put into a query for the system, which partly may relate to part of the scene, which I guess you could somehow address with attention, but it's also things like first person view of the action versus looking from the outside to the action, where you would still have the same objects and so on. So attention might not help you a lot. So I was wondering, how are you addressing such ambiguities in your embedding?
If I understand your question correctly, do you mean like so the different users may have different query sentences regarding to the like regarding to retrieval the same videos?
That could be one thing, but also if you have a rather short query, so the length of a query sentence you would typically have, there is still a number of degrees of freedom of how that could translate into video. So there is still a possibly a number of ways how this maps. So there might be not a unique text to video mapping in your joint feature space, but there might be multiple areas in the visual feature space, for example, that could map to one text query.
That's that's true. So I'm still trying to understanding your question. What do you really mean? Like so there's a like a diversity on the language side and also diversity on the video side. How can we achieve the precise matching in the joint like embedding space?
Yeah, well, I think that there is often naturally this ambiguity. So there might be two different visual representations, like you have a first-person view of a type of action that is described in the query, and you have a view of the action from outside. So videos may be quite different, and you might get kind of two clusters in your visual features or extracted action feature space, and they might map to the same textual query. So, I mean, I think ideally a user would want to get the response of saying not just a mixed list of those or kind of maximum likelihood match, but a user would expect to tell them, okay, here's these two areas which could match, and those are the videos in each of these areas of the feature space.
That's true. Like I think a video on the video side, it has more like I think it has more semantic information than the language side, because like on the language side, the query can be short, can be long, can be more like with more details, or can be very abstract. And then the user's intention probably will refer to the same video. So how can you like tell like for how can you like give feedback to the user, like why I consider this video is the like answer for your query. So I think that's also one of the research work we want to pursue, is like in addition to retrieval, we also wanted to have like a retrieval plus grounding type of like you can also not only give the feedback about the to the user about the relevant video, but also give the kind of interpretation or explanation why I think this video is related, is relevant to your query. So I think I'm not sure if that will answer part of your questions. For example, then I will precisely point to the user, okay, why I think this video is relevant to your query, because like from this region or like this interval in this video, this action or this object is related to your query, something like that.
Yeah, thank you. Yeah, I think you're right that it's. I guess it's often related to providing explanations for the response of the system, which will then the user also help to discriminate which of the possible paths forward is the one they would like to follow in querying further. Okay, thank you.
Thank you very much. So I think we're going a little over time. So thank you, Dr. Chen, and we move on to our next talk. So our next talk is by Dr. Giuseppe Amato, Dr. Mato is a research director at CNR ISTI in Pisa, where he leads the Artificial Intelligence for Multimedia and Humanities Laboratory. He was awarded a PhD in computer science at the University of Dortmund, Germany in 2002. He is external professor at the University of Pisa, where he teaches a course on multimedia information retrieval and computer vision. His main research interests are artificial intelligence, content-based retrieval of multimedia documents, access methods for similarity search, and smart camera networks. He has published more than 150 papers in peer-reviewed international journals and conferences in the areas of artificial intelligence and multimedia information retrieval with an H-index of 28. He has participated in several EC and national funded research actions in the area of multimedia information retrieval, computer vision, robotics, and cultural heritage. The title of Dr. Mato's talk is Video Search and Retrieval, Challenges and Opportunities. So that's a very interesting topic, and I'm very interested in hearing about this. Dr. Mato, if you could share your screen.
Thank you very much for your very kind introduction. I try to share my screen. Just 1 second. Can you confirm that you are seeing my slides?
Yes, they're not in presentation mode.
Yeah,
Yes,
okay. They are in presentation mode?
Yes.
Okay, perfect. Thank you very much. So I'm going to talk about video search and retrieval challenges and opportunities. In fact, this is the overview of my presentation today. But what I'm going to tell you is our experience while building the video retrieval system called Visione, which is a combination of various tools that allow you to search and retrieve videos from very large video databases. What I'm going to tell you is the experience, or the challenges and the opportunities that we had to face while building this system. And specifically, I'm going to talk about the techniques that we defined for searching by, for instance, annotations associated with videos, how to search for videos by using objects contained inside videos, how to use natural language to search for videos. This has some relationships with what Professor Jane just discussed in previous presentation. And eventually, I'm going to talk also about techniques for searching videos by using visual similarity search, so query by examples. While talking about those things, I will try to cover two aspects: the effectiveness on one side, but also the efficiency. So we try to build techniques that are at the same time effective. So you search, in fact, for what you are you want to search for, but also very fast. I mean, if you have a database containing 1 billion videos, you should search in that huge database fast in an interactive way. So we try to combine the two things: effectiveness on one side and efficiency on one side. So let me first say a few words about the Visione video retrieval system. So the overall system, as I just said, is a combination of various tools, and I'm going to tell you about 4 of the tools contained in the system, specifically the tools that allow you to search by using text. I mean, full text queries to search for videos. Techniques to search by using tags associated with videos, and those tags are generated automatically by our system. Search by using objects or combination of objects contained in a video. You can decide where they should appear on the left up corner, etc., etc. And eventually searching by example. So you have something, you already have an image similar to what you want to search for. You can use that image to search inside the video databases. Okay, this is a very quick demo of the system. There should be a video. Okay, you see, you can inside. I can add, for instance, a bounding box saying that I want a person in that position in the video, and at the same time I have a cell phone and a person in the keyframe. I can move the objects in the panel, and the query result is changed correspondingly. I can say I want just one single person, so not two persons, one single person in the video, or I can say I want videos that were tagged as mountain, or I can express a full query, a man holding a mobile phone, mountains are visible in the background, and I retrieve keyframes, and of course from the keyframes I can go to the full videos. So this is a very quick demo of what you can do by using the Visione video retrieval system, but let's go inside the techniques and the problems that we had to solve in order to build those techniques. By the way, we participated to the BBS 2019 and 2021, and the lesson that we learned is that we still have to learn more to be more competitive. So our impression is that it is not sufficient to be able to search effectively and fast, but you also need good user interface to browse in the results in order to search what you are searching for in this kind of participation. And we probably will have to improve in the browsing part of the problem, in addition to the retrieval part of the problem. Okay, this is the overall architecture of the Visione system. On the left side, you see the components that are used at indexing phase. So when you insert videos in the database, or when you process a video database and you want to extract information to be used for searching. And in the right part, you see the components that are used for searching. So we have a component which is used to extract information from keyframes, taking into consideration also relationships between objects appearing in the scene. A component for automatic image annotation, component for object detection, dominant color detection, of course, and also visual feature extraction. As I said at the beginning, we also address the problem of efficiency in addition to effectiveness. So not just accuracy, but also a system that is fast in interacting with the user. In order to represent all the information that we extract in those modules, all the information that we extract in those modules is inserted in a index which is built around the Lucene text retrieval engine. So Lucene, probably most of you already know what Lucene is. It's a text retrieval engine. You insert text and you can search documents that were inserted in Lucene. So in order to use just one single index for all that information, we used some special techniques in order to translate all the information in a kind of surrogate text representation. So, for instance, consider visual features. Visual features typically are vectors of numbers, high dimensional vectors of numbers. We represent that information as surrogate text. In such a way, we can insert this information in Lucene, and we can search for that information by using Lucene. And I'll tell you how this is done. On this part, we have the complementary to the indexing phase. So we have the searching phase. So all queries are also translated into a kind of surrogate text representation, which is used to submit queries to the Lucene index. And we will see how this is done. So we will go one by one along those components and just mentioning the problems that we solved and the tricks that we use to solve those problems. Starting from the technique for which we use to annotate keyframes extracted from videos and to search videos by those annotations. So the component is this one. So you have a keyframe extracted from a video. It goes through an image annotator, which generates a list of tags. Those tags are conveniently represented in such a way that can be inserted in a text retrieval engine inside Lucene. And on the other side, when a tag is used for searching, this is also transformed in a convenient way in order to be sent to the index. Currently, we annotate keyframes using more than 15,000 concepts. And we use a k-nearest neighbor classification algorithm in order to annotate images. You know that a k-nearest neighbor classification algorithm generates classes to the query by searching the k closest, the k most similar images to the query, and by choosing as annotations, as classes, the most frequent classes which you see in the k retrieved elements. The dataset which we used to search for the k nearest neighbors, the k nearest images to the keyframe is a subset, or let's say cleaned subset of Yahoo Flickr Creative Commons 100 million dataset. So what the Yahoo Flickr Creative Commons 100 million contains images and associated metadata. The problem is that typically associated metadata are not are noisy. So consider this example. You have a picture of a cat, and it is annotated in the metadata associated with the cat with various tags. In this case, we have cat, but we also have Taiwan, Taipei, Nikon, SIMB 200, May 2006. You can see that the only relevant tag associated with this picture is the first one, which is cat. So we defined an automatic algorithm which is able to clean the dataset just by maintaining images associated with good tags. And in a few words, the techniques is the following. We use the image is a query. We retrieve the k closest images to the query, and we look at the tags of the query, but also at the tags of the retrieved images. We just maintain pictures and tags that are consistent in queries and in retrieved images. For instance, consider the first image here. Okay, humans can see that there is a cat inside, but the tag is, let's say, useless, and it has nothing to do with the tags of the query itself. While if we consider the second image, we see that also in this case, there are several tags which are not pertinent with the image. And by comparing the tags in the retrieved image and the tags in the query, we'll see that there is an intersection in one tag, which is cat. Okay, same thing for the last image, and of course we do it for several ones. In this way, we remove images which do not have consistent tags with the query, but also we remove tags from the query and from the retrieved images which do not intersect. If we have a tag which at the same time occurs in the query, but also occurs in retrieved images, it is highly probable that that tag is relevant for the image itself. For instance, in this case, cat appears in query and in several retrieved images, so cat probably is relevant for those images. And by running this process, we go from for the entire Yahoo Flickr Creative Commons 100 million dataset to a subset of the entire dataset with cleaned images and tags. And we use this cleaned subset in order to run the k-nearest neighbor classification algorithm in order to automatically tag images. The vocabulary of tag that we have in the cleaned subset, as I said before, is more than 15,000 words. When we tag an image, so suppose that I tag this image. When I tag this image, all suggested tags are associated with a relevance score. So for instance, we have that sunset has 35.25 as relevant score, while for instance, cloud has 2.42, okay? As I said at the beginning, we insert that information in a text retrieval engine. And I think that most of you know that more frequent, frequent terms in a document have a higher rank when you perform text retrieval. In order to represent the fact that sunset is more relevant than cloud for this image, according to the relevant score, what we do is to repeat the tag several times, a number of times proportional to the score itself. So the highest score is sunset, so we repeat sunset 35 times, while for instance beach, which is here, just 2 times, cloud 3 times, and we build a document describing this image, which is inserted in the text retrieval engine. In such a way, tags. And we use Lucene to represent this information. Lucene is very fast, so even if you have billion documents, you are able to retrieve very fast relevant document according to your query. Okay. Next thing. So we discuss about how to annotate keyframes by using how to annotate keyframes in a video database. Now we go to how to detect objects inside keyframes and allow retrieving keyframes in videos according to the objects contained inside keyframes. So this is how the components are organized inside the Visione system. So we have an object detector. We have also a dominant core detection. And once we detect an object, we represent the detected object and its position in a surrogate text encoding in order, again, to use Lucene to search for this information. When from the user interface, we specify that we want to retrieve keyframes having a specific object in a specific position in the image, also the query is translated in a similar way. And so it is represented as text, and we will see how in a few minutes. And this information is sent to the Lucene index that retrieves documents that are relevant for the query. As object detector, we use various off-the-shelf object detectors. So we use YOLO, YOLO 9000, and very focal net. Sorry. So in the end, we have about 9,500 different objects that can be detected in keyframes. So, okay, suppose you have this keyframe here, and you have detected a car or a vehicle here, another car and another vehicle here, a person here, a horse here, etc., etc. Okay, that's fine. We want to represent this information in a convenient way in order to be able to retrieve this picture efficiently. What we do is to split the picture using a 7x7 grid. Okay, so the picture is defined by a 7x7 grid, and every cell in the grid is annotated with the object, if any, that is detected on top of it. So for instance, here we have car and vehicle, and those two cells are annotated with car. Here we have another car, and which more or less is here. So this cell is again, this cell contains car twice. You see car, car, vehicle, vehicle, because there are two cars on top of that cells. The same for all the remaining ones. So we have horse here, which spans all those cells here, etc., etc. Well, we want to be able to efficiently retrieve this picture if someone wants to have, for instance, a car here or a horse here. How do we do this? By using Lucene. I mean, how we can encode not just the fact that there is a tag horse in the picture, but the fact that the tag is in that specific position. So the horse is in a specific position in the image. The trick that we use is the following. So every annotation, for instance, this one person, is changed into something like this. So the annotation is person. We put in front of the word person the coordinate of where the person appears. So the coordinates of the cell where the person appears. So we have B1. So the word that is inserted inside Lucene will be B1 person, like in this case here. Here you see B1 person. So the same for all the remaining cells of the image. So the text document describing this keyframe is something like this one. See, so A3 car, A3 car. It means that in A3 we have two cars, A3 vehicles, A3 vehicles, A4 car, A4 vehicles, etc., etc. So this is the representation of the information extracted from this picture. So it is a text representation, a convenient text representation of the information contained there. When the user expresses a query, also the user query is encoded in the same way. So if, for instance, the user wants to have a vehicle in the A3 cell, his query will be encoded as A3 vehicle, and this information will be used to search inside Lucene for all keyframes who are associated with a text containing A3 vehicle, and this is done very, very fast. So let me, I try to show you on the fly an example. So for instance, suppose that, do you still see my screen?
We see the panel with the other previous, I guess we see the entire screen.
Okay, so you see the two panels. Okay, perfect. So if I take, for instance, this bottle here, and I put the bottle in this position, so immediately I retrieve all videos having a bottle in that position. Okay. Suppose I use a cell phone. I take a cell phone. I put a cell phone here, and I retrieve all pictures having a cell phone in that position. If I move the cell phone somewhere else, okay, I retrieve pictures having the cell phone in the new position. And I can also combine the various objects in the same scene. So for example, cell phone and the bottle simultaneously, okay? And I retrieve pictures which have at the same time a bottle and a cell phone, more or less in the position that I specify in the panel. Okay, I'm back to my slide. I hope you see my slide again now. Okay, so that was location search by using location of objects. Or I just discussed about objects, but you can also specify, I want a color in that specific, I want a specific color in that specific position of the image. So I want green in the top left corner of the image and red in the bottom corner of the image. But okay, it is similar to object. Now let me move to the component that allow you to search by using full text queries. And what I'm going to say has some relationship to what Professor Jean has told in previous keynote. So this, as before, is the architecture of this component inside the entire system. So given an image, we process the image by extracting relation-aware features, which are then represented as surrogate text and inserted in the index. From the user interface side, the user specify a text query, something like a dog running in the street. Okay, this is again represented as features, the same type of feature here, then represented as surrogate text, and then inserted inside Lucene in order to, and then used to search inside Lucene. In order to have this compatibility or compliance between visual information and textual information, we use a transformer encoder reasoning network, which I'm going to briefly introduce to you. So the problem that we want to solve is the following. So we have a query, for instance, a player number 8 kicked the soccer ball with his foot. And these are possible images which are compatible with this query. How do we deal with this? On one side we have text, on the other side we have images. How do we represent the information in a compatible way in order to be able to use this text to search for images? The approach that we follow is the following. We represent both features extracted from images in red and features extracted from text in green in the same feature space. And we train a neural network in such a way that if the image and the text are semantically related, the two features are one close to the other in the feature space. Let's see how we do that. We, as I said before, we used a transformer encoder network. So we used faster RCNN to identify regions and features of regions and bounding boxes from an image. This information is given to a battery of fully connected neural networks, and then the resulting vectors are given to a transformer encoder, okay, which internally contains several layers. The output of this battery of transformer encoder is given to a final transformer encoder, which has shared weights with the textual part. So I just told you what happens from the image side, but something similar happens to the text side. So we have a text describing this image, for instance. We use BERT to extract features associated with every word in the text sentence. These features are given, as for the image, to a battery of transformer encoder. And in the last step, these are passed to the last transformer encoder, which is the same, exactly the same for the visual part and for the textual part. At training time, we use a triplet loss technique, which somehow forces that the vectors which are given in output from those two transformer encoder are similar if the image and the text are semantically similar. While they are dissimilar, so the two vectors are dissimilar if the two images are not semantically related one to the other. Okay, this is the internal structure of the transformer encoder, which is rather standard, so I'm not going to describe it, also because I just have 7 minutes left. So I move forward, but if you have any question, I can go back after my presentation. Just a few words about results. This is our technique compared against state-of-the-art methods like VSA, VSA++, VSRN. And you can see that on the 1000 test set, we are always better than the state-of-the-art. On the 5000 test set, we are just better when using the SPICE method for comparing results. We use Rouge or SPICE. I can tell you something more if you're interested in this after the end of my presentation. So we, in order to further improve, we modified the basic transformer encoder that I showed you before with a adding an additional step at the end. So those two were the two transformer encoder which are shared between text and visual part. What we do is to take the feature extracted from the text and the features extracted from the image and compute a matrix having the pairwise similarity between regions and text. So for every region, we measure the similarity between the words or the features extracted from words in the text part. By adding this additional layer, we further improve the results. And by using this, we are always better than our previous methods, but also the state of the art. And by the way, this result was accepted to be published in Transactional Multimedia Journal. This is an example of matching between text and image. So the query is a large jetliner sitting on top of an airport runway. You see, these are the images, and this is the exact results given by the ground truth of Coco. You can see that it is not the first, okay, retrieved by us, but all the remaining images are pertinent as well. Same thing for this second example, an eating area with a table and a few chairs. You can see that this is the exact result from the ground truth coming from Coco, but I guess that you all agree with me that all the remaining images are relevant to the query as well. Okay, but that is nice, but we have this problem. We have a database containing 100 million videos, and I have a text query. Both are, I mean, the query is represented by a vector, and the regions are also vectors. How do we search quickly for the image relevant to the query, given that we have a huge database? Also, in this case, we used a special encoding of the features and extracted from the visual part and from the textual part in order to allow this information to be represented inside Lucene and to be searched fast. So I move to the last part of my presentation, which is how to support visual similarity search, or let's say also cross-modal similarity search. I'm going to tell you about a text encoding method that we define, which is based on scalar quantization. Okay, so you have a deep feature, for example, a very high dimensional vector of numbers, something like 4,000, a vector containing 4,000 dimensions, for instance. What we don't want to do is to represent this vector in a convenient text format in such a way that it can go inside Lucene to be retrieved fast. An important point to keep in mind is that typically text retrieval engine work well because they index sparse vector. I mean, when you insert a document, a text document containing natural language text, of course, inside a text retrieval engine, the number of words contained in that document is much smaller than the entire vocabulary. So for instance, I mean, if I index a scientific paper, I might have, I don't know, something like 1,000 different words, for instance, but the English vocabulary is much larger. So you just index the document by using 1,000 words. The problem is that when you have a vector of features, you have a very dense vector, not a sparse vector. All elements of the vector have a value. There are no zeros which can be ignored typically. So we first need to transform a vector in something that is sparse, and then represent this in a convenient textual representation. So first thing, let's try to move from a deep feature, so a very long vector of number, into something which is sparse. In order to do that, we first apply a random orthogonal rotation to the original vector. In this way, we distribute variances much better in the various vectors. And second, we apply a concatenated ReLU on the vector. So a ReLU put to 0, everything is negative. So what we do is to concatenate all positive value and all negative values into separate part of the vectors. Okay, so for instance, by doing this, you can see that we have vectors which contain some positive value and some values that are forced to be 0 just because so this is already a bit more sparse than the original vector. In addition, we add some quantization threshold. So something, everything which is smaller than a certain threshold is put to 0, and we have a sparse vector. Then this sparse vector is transformed into a surrogate text representation. So for instance, in this case, we have that the first element of the vector is 21. So we repeat the word, or let's say the word representing the first element of the vector 21 times. The second is 45, so we repeat it 45 times. This is 26, we repeat it 26 times. So this is the text document that we insert inside Lucene. And we use the cosine similarity in order to compare different vectors, or let's say to use a deep feature as a query into a database containing billion features. And this is very fast again. That's also, I am at the end of my presentation. I went through the some of the components which are inside our Visione system for video retrieval. And I tried to quickly summarize some of the challenges that we had to face, not only on the effectiveness aspect, but also on the efficient aspect. There are some, say, as I was saying at the beginning, there are some lessons that we learned by participating, for instance, at VBS. We overlooked the importance of the user interface. Currently, as you have seen in my demos, the user interface is very simple. So you can drag objects, and then you see a very simple list of results. For instance, you have to scroll down in order to check if what you are searching for actually appears. So we don't have any clear functionality for browsing results. And I think we need to devote some additional effort, not just on the retrieval capabilities, but also on the browsing of results retrieved. In addition, currently, we just work on images, so on keyframes extracted from videos. The challenge that we want to address in the next year is to move from images, or let's say to complement images with videos. So take into consideration the action that appears in a video, not just the static information contained in one single image. So looking at recognizing what happens in a video. So the action, the time interaction between objects appearing in the scene, etc., etc. But this is future work. So I'm at the end of my presentation, and if there are any questions or any clarification, I might be happy to answer to them.
Thank you very much, Dr. Giuseppe. So do we have any questions?
Yeah, hi. I have one. Thank you for the great, interesting presentation. One quick question about the current system as you described it.
Hello?
Does it? Yeah, can you hear me?
Can you repeat, because I think I lost 10 seconds of your question.
Sure. Yeah, I was saying in your current system that you described, do you handle any motion information? Encoding, perhaps, or is it just location and color?
Yeah, actually, as I was briefly saying in the conclusion, currently we just use images, not time. So just information in the space in one single keyframe, but there is no information, there is no time-related information that we take into account. So we do not consider actions, but this is what we want to address in the future. So trying to extract information that is time related, not just space related. So we currently do not have this.
Okay, thank you.
So if I could just ask another follow-up sort of a question. So if you're looking at the keyframes and the spatial information, how many keyframes in general do you use per video? Is it just a single one? And so if the video is slightly longer, do you use multiple keyframes to figure out if that spatial information and the query spatial information is actually available in the video?
Actually, the, let's say, key frame extraction is something that can be configured. So it depends on the final application. For instance, in order to participate in VBS, we use exactly the keyframes that were provided with the data set given by the organizer of VBS. But we might also run additional keyframe extraction in order to increase the number of keyframes. So this is something that can be tuned. So there is no, let's say, a single answer to this. The more keyframe, the better. But for instance, in VBS, we participated by just using the keyframes that were already given to us by the, that were already contained in the data set provided to us.
Okay, thank you.
So as far as I know, it is one keyframe per shot. And when the shot is too long, there is some additional keyframe in the middle.
Thank you very much.
You're welcome.
For your time, and I think we can now move on to our next presentation. So the next presentation is actually going to be our first oral presentation. It is from the Renmin University of China. The paper is by Aozu Zhen, Fanzhu, Zihong Wang, Fangming Zhu, and Zirong Li. The title of the paper is What Matters for Ad Hoc Video Search, a Large-Scale Evaluation on TechVid. Please go ahead and start your presentation.
Okay. So can you hear me?
Yes, we can hear you.
Okay. Now I can share my screen.
Yes, please go ahead.
Oh, okay. Okay. Thank you. So can you look at my, see my screen?
Yes, we can see your screen.
Okay, so, okay. Hi everyone, I am Ao Chen, a PhD student at the Ming University of China. Today, I'd like to share with you some of our findings in ad hoc video search and try to answer the question, what matters for ad hoc video search? So, okay, what is ad hoc video search? As shown on the left on this page, given a text query, the system returns several videos that best match the text query from an unlabeled video data. And there has a lot of work effort on how to build such a system. A high-level view of those methods for IVS can concluded as three-dimensional. How a text query is represented, and how an unlabeled video is represented, and lastly, in what feature space cross-module matching is performed. Well then, how to measure the performance of those methods in real-world situation? I think it's a difficult problem. So to meet the problem, NIST holds the check-weight ad hoc video search evaluation run annually since 2016. Given the text collection and a set of ad hoc queries released by NIST, return for each query a list of at most 1,000 short IDs from the text collection ranked according to their likelihood of containing the text query. The results were judged by NIST censors, and the official performance metric is inferred average precision. As for the text collection, the ICC point 3 is a text collection of check-weight IVS 2016 to 2018. The size of it is 336,000, which increases to 1 million of which increased 1 million for check-weight IVS 2019 to 2021. So anyway, thanks for the efforts. Thanks for the efforts. Thanks for the efforts carried out by the list check-weight, the IVS benchmark. The progress in ad hoc video search has been measured. So next, I will briefly introduce the winning solutions in recent years. As shown in the table, there have an overview of top performance system in check-weight 2019 to 2020. Because the text encoder is often considered in the signing of cross-module matching models. There we do not compare text features deliberately. On the other hand, as check-weight does not specify training data for the IVS task, so we take into account the training data and the pre-training data. It can be seen from the comparison. The solution often vary in terms of the choices of cross-module matching models, visual features, and training data. So what matters for IVS? Towards answering the question of what matters for ad hoc video search, we evaluate solutions for AVS in 3 dimensions, matching models, video features, and pre-training or training data. Then present a large-scale impression study on the track video AVS benchmarks in last 5 years. They're namely TV16 to TV20. To bridge the gap between the current solution level comparison and the desired component-wise comparison. Furthermore, for the sake of reproducibility, we opt for open source models, visual features extracted by public pre-trained models and public datasets. First, the model 2, we saw the graph according to the parameters and time of publishing. We select the following 5 models, W2, VV++, C, MM, and DE are used in the previously winning solutions. And the MMT and Clip have competitive performance on the video text matching task. In addition, we have invested 2 variants of Clip and C, namely Clip virtual relearning and C Clip. Improve C by submitting Clip by GRU is C Clip. Next, as for the visual feature pool, we use we collect 7 state-of-art deep visual features, 4 of which are 2D features. It could also be defined as frame level features, 3 of which are 3D feature. It could also defined as segmental level feature. Furthermore, we use a single vector connection strategy for feature fusion to get the combined feature. As for the training and pre-training dataset, 5 datasets that were used by participants of the track video AVS task. The MS COCO and the GCC are image data. We use both for pre-training, and the left is video data. We use those 3 for training. An exhaustive combination of the varied models, features, and training data is conventionally prohibited. So we have to be selective about the choices of AVS solution to be evaluated. As for experiment 1, in order to compare different models, we use Clip as the fixed feature for its effectiveness and efficiency. The MSRVTT and TGF as training data. Look at this table, we can find that both Clip feature relearning and C Clip outperform than 5 open source models. As for experiment 2, comparing visual feature, Clip feature relearning can only use Clip feature, so we use the second performance C Clip in preliminary experiments as a cross model matching module. As shown in the table on the top of this page, we can find the 2D deep features are in general better than their 3D alternatives. When used alone, and the WSL is the best. As shown in the table on the bottom of this page, after additional use C3D of the calculation of RX101 WSL and CLI, increasingly infer AP from 0.201 to 0.212. The 3D features remain, it shows that the 3D features remain beneficial when used together with the 2D features. And the combined feature gives the best performance in all the text features. Lastly, when considering the joint of the multiple pre-training or training data set, we use C-clip and the best combined feature, namely concatenation of RX101, WCL, clip, and C3D. As shown in this table, comparing rank 4 and rank 2, we can find adding my text to the training data can bring improvement. Comparing rank 3 and rank 1, pre-training the model on MS COCO, followed by fine-tune on MSRVTT, TGIF, and Vitex brings a marginal improvement. And the relative lower performance of rank 3 with the infer AP of 0.23 shows that GCC is less effective than MS COCO for pre-training. Okay, summary and conclusions. After a large-scale evaluation on the track-weight AVS 2016 to 2020, we found the C-clip shows the best performance in all models. If you want to get started AVS task, maybe you can start here because the model is open source. And if you already have a cross-module matching model, you might as well trying to use the combined feature or better feature fusion method to improve performance. In addition, it's also a good choice to use image data to pre-training the matching model of AVS. Okay, that's all. Thanks for your listening.
Thank you very much. Do we have any questions? Okay, so let me just start. So you said that feature fusion is very important. What method of feature fusion did you use for these experiments?
What?
Like, how did you use the feature fusion?
Actually, we just use simply vector concatenation. Maybe later we can try have attention module or something else. We just used the vector concatenation of the various feature.
Okay, thank you. And how long did it generally take you to train all these systems?
It depends the training date. If you use the MSRVTT, TGIF, and Vitex on C-clip, maybe need 6 or almost 6 hours. It depends on your machine. If you have 3 or 4 GPU, like 2018 Ti.
Okay. All right, thank you. I do not see any more questions, so we'll end this presentation here. Thank you very much. We did run over our time just by a little bit, but luckily we do have a break coming up, which will allow us to make up for it. So we will meet at 10:30 Eastern time, which is in 17 minutes. So I hope to see you all here. We'll have 2 more oral presentations, followed by an invited talk by Professor Dima Damon, who is also a program chair here at ICCV this year. So I hope to see you guys in about 15 to 17 minutes. Thank you. So welcome back. In the interest of time, I think we'll start. So our next paper is to be presented by authors from the Beijing University of Posts and Telecommunications. The title of the paper is Instance Search via Fusing Hierarchical Multi-Level Retrieval and Human Object Interaction Detection. The authors are Wen Hao Yang, Yinan Song, Zicheng Zhao, and Fei Su. Please go ahead and start your presentation. Do we have the authors from BUPT available? Okay, so I do see one of the authors here, but I'm not sure he's not responding at the moment. Maybe there's some technical issues. George, do you think we can move on to the next presentation first then?
I think, yeah, let's do this for now. Yeah.
All right. Okay, so we'll move on to our third oral presentation. Let me just check if Damianos, are you ready to present?
Yes, hello. Can you hear me?
Yes. Okay. So let me
Okay,
just
yes.
give you an
Yes, I'm ready.
introduction. All right. So our third paper is hard negatives or non-negatives, a hard negative selection strategy for cross-modal retrieval using the improved marginal ranking loss. The authors are Damianos Galanopoulos and Vasilios Mizares from the Information Technologies Institute, Center of Research of Technology, Hellas. Please go ahead.
Thank you. Let me share my screen. Okay. Can you see my screen?
Yes, we can see it.
Okay, nice. Hi, my name is Damianos Galanopoulos, and I will present our paper, Hard Negatives or Non-Hard Negatives, a hard negative selection strategy for cross-modal retrieval using the improved marginal ranking clause. As you know, cross-modal learning recently has gained a lot of interest. The most recent approaches use deep network architectures, and trainings performed using the improved marginal ranking loss or similar losses. These approaches rely on hard negative samples mining during the training. And for this, we focus on extracting actual hard negative samples. More specifically, we focus on samples that are semantically close to the anchor sample and should not be considered as negatives. Moreover, we examine different strategies for efficient combination of multiple models. Here you can see an illustration of the problem statement. Considering as anchor the video caption sample A, with a caption, a fast car is racing around a track, and two additional samples, B and C, in which sample B has a caption, a fast car is racing down a track, while sample C has a caption, fast cars are shown off at a show. So which one of B or C should be considered as a hard negative sample? Typical hard negative mining approaches will select sample B because it's the closest to the A, but clearly this is a positive sample. On the other hand, sample C, which is the second nearest to A sample, is similar to A, but clearly is a negative sample, and this sample should be considered as a true hard negative instead of B. As a starting point, we utilized an attention-based dual encoding network to learn a new joint embedding space. The network consists of two similar subnetworks, one for the video stream and one for the textual. And each subnetwork consists of multiple levels of encoding. Following state-of-the-art approaches, the improved marginal ranking clause is used to train the entire network. The combination of multiple models is known to lead to improved performance. So we train 24 different models by modifying the following parameters. We have two positions in the architecture for inserting the attention mechanism, one for the textual and one for the visual. Two different textual encodings are used, BERT and a combination of walk-to-vec with BERT, two optimizers and 3 learning rates. The resulting 24 models are combined in a late fusion scheme. In order to mine hard negative samples, we design an offline-online strategy to exclude potentially positive samples. At the offline stage, we estimate a threshold P for the similarity of samples so that only samples with a similarity smaller than this value P will be treated as hard negative candidates. First, we randomly split the training dataset into batches as we done for training. And in each batch, the cosine similarity between all possible caption pairs is calculated. And after this calculation, within all batches, we assume that a value X%, for example, 1 or 2%, of them indicate very similar samples. And for this, one could not be treated as a hard negative for the other. Finally, the similarity threshold P, of which X% of the similarities are higher than value P, is undefined. At the online stage, during the training, we enforce the previously calculated value P, and in every batch for a non-core sample, every other samples within the batch with a similarity bigger than value P is not considered as a negative at all. Every other sample is labeled as negatives, and out of this subset of samples, the sample with the highest to the anchor similarity is selected as a hard negative sample. The combination of multiple models is known to boost performance. So following the proposed hard negative mining strategy for different plausible assumptions about X, for example, 1 or 2%, due to different p-values, the number of available models can be quickly increased. So we study a combination of multiple trained models in a late fusion scheme. And for this, for a given query, every trained model results in a ranking list of the most relevant videos. So we examine 3 different strategies for combining this ranking list, which are the average, the max, and the hybrid one. At the average strategy, we assume that every model is a well-performing one, and we treat them all equally. So for a given video, we average all rankings of this video. So this and the finally ranking is extracted from this averaging. On the contrary, we can assume that not all of our models have very good recall, but we assume that at least the samples they place at the very top of the ranking list are true positives. So if a video appears very high in the ranking list, generated by at least one model, we trust this video to be a good answer for our query. But of course, neither of the previously 2 assumptions seems perfectly plausible. In our hybrid strategy, we select the Q-dash ranking list for a retrieve video, where the video is ranked the highest among all of Q total ranking list. So these top Q-dash rankings are averaged to calculate the final ranking for this video. And finally, all retrieve videos are reordered according to their final rankings. So we think that if at least the Q-dash models bring a video high in the ranking list, we trust this to be a good solution for and a good answer for our query. And of course, there are some special cases. If Q-dash equals Q, the hybrid approach is the same as the average, while if Q-dash equals with 1, the hybrid approach is the same as the max strategy. Moving on to the experimental section, we train our model using 4 large-scale datasets. We use the V3C1 evaluation dataset using the providing from TrackVid queries for the AVS tasks for the years 2019 and 2020. And of course, as in the AVS task, the mean extended inferent average precision is used as evaluation measure. Also, we, as initial keyframe representation, we use features from ResNet for the network of ResNet 152, trained on ImageNet 11K dataset. So in this slide, we can see the results in terms of mean extended inferent average precision of the combination of multiple models and different setups. We illustrate comparisons between the baseline hard negative mining strategy and the proposed one with X 1% and 2%. And moreover, the last row shows the results when all models from every mining strategy are combined. We can see that the proposed hard negative strategy using X equals 1% slightly improves the performance on both evaluation dataset, however, following any fusion strategy. Regarding the hybrid fusion strategy, it performs considerably better when a plethora of models are available. And setting Q dash equals 10, the performance increases to 0.1537 from 0.1492 on the AVS19 dataset, and to 0.2416 from 0.2304 on the AVS20 dataset. In this slide, the results of the evaluation datasets for the hybrid strategy and different Q values are illustrated. We can see that when we combine multiple models, the performance increases immediately. For example, when Q dash equals 2. And there are a sweet spot between 5 and 25, where the performance is generally stable and is maximized. As more and more models are added, the performance then starts to decrease until it becomes equal to the score obtained by the average strategy. So to sum up our work, we proposed a new strategy for hard negative mining to improve the performance of a cross-model video retrieval network. And for this, we focus on excluding positive samples for being wrongfully utilized as hard negatives. We propose a hybrid strategy for model combination to take advantage of the high number of trained models that we have. And the new hard negative mining strategy gives us small improvements, but in combination with a hybrid fusion strategy, the performance is further boosted. So thank you for your attention. If you have any questions.
Thank you very much. Do we have any questions?
I actually have one.
Mm-hmm.
Yeah, hi. Thanks for the talk and the paper. I was just wondering, given that you found out that you only need probably between 20 to 25 models to reach maximum performance rather than going all the way to 70.
Mm-hmm.
Did you check across TV 19 and 20? Are those models consistent between these two data sets? Are they the same, or which models are they?
No, actually, they are different models.
Okay.
It depends on the evaluation dataset. We have also results on AVS 16, 17, 18, which different model perform better to one dataset rather than to another. So the well-performing models to 2019 are not the same with when it comes to 2020.
Right. So it seems like a generalization problem or something. Sure.
Mm-hmm. Probably.
Thank you. Thank you.
We also have a question from Werner. If you could unmute yourself.
Yeah, thank you. So I was wondering the percentage of nearby still positive samples. Did you look into this, whether this is very query dependent, or is there a percentage that holds for a larger number of queries?
Are you asking about the hard negative selection or the
Yes,
fusion?
yes, about the exclusion of the positive samples that you do.
Mm-hmm.
So I'm wondering, is there a lot of variance between different types of queries? So do you have a larger percentage of those that should still be considered positive for some queries and a very small one for others?
Generally, yes. At every batch, the number of exclusions, it depends. In some batches, maybe 0. In other batches, it can be 3 or 4 or 5 samples that are excluded from the negative pool.
Okay, yeah. Thank you.
You're welcome.
Okay, thank you. So we're having some issues connecting with our third speaker. So George, but we do have a video from them. So George, could you?
Yeah, sure. Can we do we have confirmations that they can't present?
I've been unable to get any response. They're here, but I'm not getting any response from them.
When Ho Young, can you hear
Yes.
us? Okay, let me try to pull the video and share my screen.
Good morning, everyone. I'm up.
So okay, I think I will need to quit the Zoom and rejoin again to adjust the permissions of the Zoom.
Okay. To everyone here, I sincerely apologize for this, but yes, sometimes it's just not possible to get everything right. Murphy's Law at work. Some of the issues that we have with virtual workshops and conferences these days. We'll just wait for George. Nina, are you sharing your screen? Are you doing it by accident?
I would say if the video is already up and pre-recorded, do you really want to show it?
Well, I think we have one of the participants here because I see that they're sharing the presentation. Nina, can you hear me? Are you sharing the presentation right now?
No, sorry, Asad, this is me still, but it's my account my computer has different accounts.
I see. So yeah, George, would you think that having the video there, we can just move on to, because we're almost at 11 anyway, because of the.
Yeah, let's do this. Okay.
So we can just move on to
Right.
Professor Damon's presentation. Okay.
Sure. It's just that, you know, if it's there, people can always watch it later, right? We'll finish it
Right.
earlier.
Yes. Yes. Thank you. So let me just give the introduction. All right. So our final invited talk is by Professor Dima Damon. She's an associate professor in the Department of Computer Science at the University of Bristol. Dima is currently an EPSRC fellow, focusing her research interests in the automatic understanding of object interactions, actions, and activities using wearable visual and depth sensors. She has contributed to novel research questions, including assessing action completion, skill, expertise, determination from video sequences, discovering task-relevant objects, dual domain and dual time learning, as well as multimodal fusion using vision, audio, and language. She's the project leader for Epic Kitchens, the largest dataset in egocentric vision and accompanying open challenges. She also leads the Epic annual workshop series alongside major conferences such as the CVPR, ICCV, and ECCV. Dima is the program chair for ICCV 2021, associate editor of IJCV, IEEE PAMI, and pattern recognition. She was selected as a Nokia research collaborator in 2016 as an outstanding reviewer in CVPR 2020, ICCV 2017, CVPR 2013, and CVPR 2012. Dima received her PhD from the University of Leeds in 2009 and currently supervises 7 PhD students and 5 postdoctoral researchers. The title of her talk is From Narrations to Semantic Similarity for Cross-Modal Video Retrieval. Over to you, Dima.
Thanks a lot for the detailed bio and for the invite. So I'm really excited about the workshop's talk, the workshop's title, the limitations of current cross-modal video retrieval, and I hope to be able to touch on that, going basically into some directions that will give insights, I hope, to people attending the workshop. Right, so I think you're all familiar with cross-modal video retrieval, but just to make sure that we're all around the same terminology, especially the types of videos that my group has been working with. So we have these short clips, right? And these short clips are described by sentences like putting the garlic down, and the modalities we talk about are typically the video modality and the text modality, right? And we focus on cross-modal because we are interested in both tasks. The video to text retrieval task, that's when you query with a video and you are then having a gallery or a set of possible text, sentences, captions, and you wish to rank these, and hopefully you want your correct caption to be ranked as highly as possible in this predefined gallery or retrieval set. Then, of course, the other direction is to go from text to video. That is, we're given a text and we want to search a large gallery of videos or retrieval sets to come up with the answer. And talking to different collaborators or different people, they seem to find one or the other of these more natural or more interesting. I get lots of people telling me the second one, the text to video, is the main one. That's because there are lots of videos we don't want to look at and we want to query using sentences. But also the people doing video captioning or video understanding focus on the first one. These cross-modal video approaches tend to be able to perform both. They don't always get evaluated on both, but typically these retrieval spaces, they have both modalities and they could be used to do video to text and text to video. And unfortunately, we don't have a very good understanding in the community about which ones we're interested in. You see some papers or some data sets only reported or evaluated comparing to only one of these two tasks. So where do these videos and texts come from? And I think this is important to bring to the forefront of the discussion because I think they differ. So video to text retrieval isn't the same, regardless of whatever the video source is. So maybe the typical video source is a gallery of videos like YouTube that you want to rank. But there is also the notion of a video stream, where you want to retrieve a clip of that stream, often referred to as moment retrieval. Note that the approaches tend to be the same, whether you're doing the first or the second at the moment. Or of course, you have combinations of the two. So you have longish videos and you want to retrieve a clip from one of these videos that is relevant to the query, say text you're doing or whatever, another direction. And our current datasets are a mix of both. And again, as I said, we seem to be treating them exactly the same regardless of the source. In my head, they can't be, the methods can't be the same in these different video sources. Where does the text come from? And again, we have a mix of these two text sources that we seem to not distinguish very well, or maybe I'm trying to kind of show you the distinction, and let's see if you agree. So there are captions or text queries. These tend to be a little bit more detailed, where people are asked to describe everything that happens in a video clip. They tend to be a longer sentence of, say, 15, 20 words, maybe a bit longer. But there are also an increasing interest in these narrations or subtitles. These tend to be a lot shorter because they're not intended to describe everything that happens in the video. They're intended to give a narration alongside an ongoing action. So some of these, so they're describing some aspects of the video and they tend to be a lot shorter in the description. My group's interest tends to be in this latter narration subtitles, which are shorter and which are, in my opinion, harder for the retrieval task due to their, approaches being actually descriptive of some of what's happening in the video and a lot shorter in the text description. Right, so with these video sources and text sources, I tried to kind of put some of the data sets that we all play with into this table that describes the video gallery, the one video stream, and the clips, and some of the data sets. Most of the data sets are caption based, even data sets that come from YouTube, like YouCook2, where the narrations that come from the YouTube are not used, and then they're captioned again by someone describing what's happening in the video. As I said, my interest, because of my involvement in Epic Kitchens and also Ego4D, which I'll tell you a little bit about, is more on the narration side, which I believe is a lot more scalable to collect, but has its also challenges due to the short nature of the narrations. But again, when we talk about text to video retrieval, you might pick a paper and it might be in any of these categories, and hardly, you probably need to dig deeper to understand where does it belong and what aspects can it cover. In this talk, I'll take you through 4 steps out of my research interests, particularly on collecting narrations, then into semantic similarity in retrieval. The first 2 are really limitations of current approaches to video retrieval, and then some of the solutions, particularly disentangling the retrieval space, and I'll tip onto retrieving by behavior rather than by a text query. Right, and let's start by collecting narrations. That's the thing that got me really excited about retrieval and getting all those very, very scalable narrations. And this was part of a project that we started now 4 years ago. So Epic Kitchens currently is 100 hours collected by giving people cameras to take it to their homes to record what they do in their kitchens in a completely unscripted manner. So while they're recording, there are no narrations and there is no predefined script or text. Of course, one of the challenges in collecting such a free-form set of videos is how will you even be able to do any ground truth in them? And that's where the narrations come to play. And I'll start by just acknowledging that this is a collaboration between Bristol, Catania, and Toronto over the past 4 years. So indeed, we gave people cameras, but all with the intention of being able to do something with the data. And thus we came up with this idea that we stole from many people who are using movies as data sets, where movies come naturally with subtitles. And here, people to then give us narrations while watching the videos post-recording. We're calling them live narrations, but that always causes confusion to people. They're not while the people are doing the cooking action, they're actually after, but people are talking over and describing what they're doing as they watch the video. These are then subtitled, written down, translated if needed, and then are formed into these dense action segments that form clips. That was the first round that resulted in the first version of Epic Kitchens. We then extended the data collection, changed the narrations a little bit, and I'll tell you about that because that's where the timestamp narrations are coming from, and then improved these annotations. And as I said, we now have 100 hours, which up to the end of November, because Ego4D is not yet out, is the largest data set. But now we have been working with a consortium of 13 universities and Facebook AI to release Ego4D, which again, I'll mention a little bit shortly. So these are the type of narrations that I talk about. They tend to be the same as your subtitles of a YouTube clip, but these are actually activities of daily living, like someone opening a cupboard or picking up tofu or putting something in the bag. They tend, accordingly, what you have is one moment in time and a short sentence describing the action. And as I said, in our data set, it could be in another language, but you also have them translated should that be needed. So we then went and did this start and end time in alignment with the vision community, because these single timestamps aren't really something we in the community are very familiar with. We don't know when the action starts and ends. We want a clip. We want to query with a clip, and we want to retrieve a clip. And doing this mapping between these single timestamps and clips, and this visualization highlights one of these difficulties in video retrieval, which are the variation in length of daily actions. Some actions are really, really short, like taking a paste, and some action like squeezing the kitchen towel onto the tofu that is taking longer. And we currently expect methods to deal with both of them, understanding the start and end times. So this is just to show you the type of narrations or subtitles that we have or we've been playing with. So you see the subtitle or the narration coming between the time it's happening to its end, right? Some, like turning the pizza on the right, is taking longer. Others are shorter, and I'm slowing these down for you to actually see. This is also from a bunch of people preparing coffee, and you can see the variety in how people do stuff. Some are using machines, some are using aeropressors, etc. Right? But we are here in the fine-grained nature of inserting the coffee holder or emptying coffee, right? And again, I want to emphasize the variation in the length of these clips. We have been collecting these narrations using a publicly available tool that we made available, which allows people to then watch a video and basically talk over it, but also ensure that what they say is aligned in time with the video itself. So the person is now recording a short narration of, put down pita bread, and what you see on the right are these single things. And what you see here are these small timestamps that get built over time. And if you see a video that is nearly completed, you see how dense these narrations are. In fact, they are here up to 20, I think on average, is there 20 sentences per minute. So there are a lot, really, really short clips and short sentences, but fairly detailed in time. So yeah, people can narrate, they can pause the video when they're narrating, and they can eventually sync the narrations to the videos. And then from these narrations,
adjust temperature on hot.
Big coffee pot. You get people to transcribe, and one of the approaches we used is also to make sure that people have access to the visuals, because some of these words don't get correctly recognized when you hear the narration if you don't see the visuals in action. So this is Epic Kitchens and how we collected narrations in Epic Kitchens. Similarly, and I think this is the exciting aspect, is now we have more of such narrations in a variety of scenarios. Ego4D as a project was just launched this Thursday. It's 3,000 hours of egocentric video. And as I said, it's a large consortium of universities that have worked to collect all varieties of daily action activities, all using egocentric cameras. And tomorrow at the Epic workshop in the afternoon, we will be having a reveal session where members of the consortium will tell you about the dataset and its challenges. The dataset itself will be available for download end of November. But also the narrations in Ego4D have been inspired by the Epic Kitchen's narrations, where narrators were provided the following prompt: pretend you watch a video, and then you're talking to a friend of the phone, so you describe the events, but your friend cannot see the video. And similar to our pause and talk narrator, when they would pause a video, and here they were typing a sentence such as this. So you'll have, C leans on a table, or C kicks the ball, or C opens the box, where C in this case is the caption describing the camera wearer, because Ego4D isn't only a single person, so you might be describing the action by someone else with a different hashtag. Let's see some of these in action. And you see these short descriptions again with a single timestamp. So there are no start and end times, describing 3,000 hours of activities collected in 9 different countries, 74 different cities, by 855 different camera wearers, and in total about 4 million sentences. Right, so this is Ego4D, this is Epic Kitchens. All sounds very exciting. That means more and more we're gonna have lots of these narrations. These are also very similar to the narrations you might find in YouTube, subtitles, but we do not have start and end times. We don't have this notion of clips that we for years have relied on. Clips or start and end times are very, very expensive to collect. So what can we do with these single timestamps so that we can leverage this huge resource without actually having to then annotate start and end times? It has to be sufficient that there is a location in the video aligned with the action that describes what's ongoing without having to then label start and end times. And this is really something we've started a while ago, so I don't have an answer for this, but I'm here to show you a paper from CVPR 2019, where we tackled the single timestamps. So starting from the description, what we want is to start from these single timestamps, maybe have some sort of a clip level structure saying it's probably here, then adjust those locations so we end up with something that actually is well aligned with the action and describing the action. So this is again a work by Davide, myself, and Sanya Filler from Toronto. How did we do that? So basically we start with this single timestamp and with a preset length clip, call it. Then here we were training a classifier for these actions. So we were parsing the sentence into a verb and a noun, actually figuring out the class, and then training a classifier. At the beginning, the classifier is really bad because it's learning from noisy data. But hopefully there is enough alignment across the various examples because we're basically taking frames from this initial proposal and training a classifier. Over time, these proposals get adjusted until at the end, not only we have a confident classifier, but also a localized. So we move the sentence, basically. We move the sentence, which in this case is opening fridge. We move it from its initial timestamp to its best localized place in the video. I'm not claiming this is the best approach because this is an expensive process, but it does work. And this is an example where I'm showing the initial proposal. The initial proposal is in the dotted line. The ground truth is in the thick line, and you'll see these proposals moving from the initial approach into their final location based on this iterative learning process. And importantly, you'll see the example. So this is an example of opening the drawer, and you'll see how well aligned it is at the end, taking glass, and then how it's well aligned at the end. So the bottom row is really the exact location of moving bottles. It's actually tighter than our usual start and end times. They tend to be a lot tighter then. Let me show you another example. I'll just move a little bit. I think this is a long one, but this is an example of opening cupboard. Yeah, and this is the original example, which was quite far, and this is the eventual one, right? So we can learn with single timestamps. That's one of the limitations currently of video retrieval, the need for a clip. And many approaches actually are trying to do single timestamps. The How to 100 Million is trained from noisy data with single timestamps. The visual grounding approach also from DeepMind. There are approaches to use single timestamp now for localization inspired by our work, and also another work I'll talk about later on action modifiers. And I'm sure there are more I haven't mentioned, but when we talk about limitations of video retrieval, I would claim that if we move away from clips, we would free ourselves into a bigger potential of resources for video and text descriptions. Right, so this is the first bit where I told you about narrations, how we can collect them, and how we can use or utilize a bigger bunch if we stop relying on these clip level start and end times. Second in the talk, I'll present a paper we presented in CVPR on semantic similarity in video retrieval. And you're all familiar. This is actually from MSR-VTT. Yeah, it's from, I was thinking you could know, from MSR-VTT, and the video on the left is the query, and the 4 texts on the right are some of the gallery, some of the texts in the validation set. And of course, you would be, the methods, the best method is the method that's able to highlight or retrieve the sentence, "A man is peeling fruit carefully and neatly," as the best one. Of course, when we dig deeper into these data sets, which again, I know many of you are familiar with in terms of numbers or in terms of state of the art, but here we're looking at what really these data sets contain. This is again from MSR-VTT, where this video on the left is in the test set in terms of a query, and the 4 sentences on the right are actually descriptions of 4 different videos in the test set. One of these is the ground truth, so is the text associated with this video, and 3 are not associated with this video, and thus are considered incorrect, right? So the example of a guy explains the steps of folding paper is considered incorrect, while actually the man performing an origami tutorial is actually the correct one. All the other ones are considered incorrect. This is present throughout the video retrieval datasets that we're familiar with. So this assumption that exists only one caption, this is the caption that's corresponding to the video, and vice versa. And this assumption is used in training, but worse, is used in evaluation. So you'll see UCOOK2, and the video on the left is tied with the bold caption, first one in the list, but the other 4 captions do exist in the test set. And should you, by bad luck, retrieve the caption, "Peel and cut the potatoes into chunks" first, your method is going to be considered worse than the method that retrieves "peel and chop potatoes." Similarly, in MSR-VTT, you'll see that this video on the left, the actual correct ground truth is a band is performing for the crowd. I think the last one is much better, 3 guys singing and playing instruments on a stage, because I can't see the crowd in the whole clip. And Epic Kitchens, if we had used it as a standard retrieval dataset, would have the same problem, because we have lots and lots of descriptions of exactly the same action, putting spoons in drying racks or bowls or plates or forks, and one of them is considered correct and the others are considered false. Okay, a problem. So this is clearly a problem in current video retrieval methods. What can we do about them? Of course, it would be ideal if we can relabel the whole datasets by establishing the link between every video and every caption. But that's very expensive and we think is unnecessary. We start by the assumption that the corresponding caption is sufficient to describe the video. And thus we look at the relationship or the similarity, what we call the semantic similarity, between the caption considered as ground truth because it was collected with the video and the other captions in the dataset, right? So if these are very similar, then we consider that they should be acceptable as a retrieval text for that video and vice versa. Remember that this is being done cross modalities, so text to video and video to text. So if this is the standard current approach to video retrieval, where one caption is considered correct, we use semantic similarity to find the other corresponding captions that really match that one. And then we consider all of them as correct. This allows us to evaluate an error bar of methods that retrieve. Where do we retrieve all of these captions? Where is the highest one? Where is the lowest one? And then we look at our methods and some of the methods out there This is on UCOOK 2. And we compare a simple MME, that is purely a fully connected projection layer for text and video, with more advanced methods that have been proposed over the years and have, as you can see from without the error bar, claimed to be outperforming the ground truth by a big margin. If we add this error bar, then things are quite different. And that's the same in all the other data sets. And as I said, EPEC has a bigger bunch of that. Maybe that's how we identified all these issues, because we have even more similarities in the domains within the data set. But still, large-scale data sets like MSRBTT suffer hugely from this semantic similarity concern at the moment, and we hope to turn it into potential. So instead of just having this cut threshold, so this is a threshold that says, yes, they're exactly matching, or no, they're not matching. We move into a basically a soft assignment where we calculate the similarity between the sentences. That means some texts might be more similar to others. If you're peeling potato on the left, you would consider an example of someone peeling onion to be a lot more relevant than maybe someone washing a dish, right? Because there is some still similarity either in the verb or in the noun. You can look at the paper in details because we propose 4 different proxies, depending on the objective of the retrieval task, that then assigns a similarity between the video and the caption based on the text-to-text similarities. And these 4 captions, which are based on back of words, part of speech, synsets, and meteor, if you now look at the simple baseline and the 2 more advanced baselines using instance versus using these other approaches, actually, in some cases, the simpler baseline is outperforming these methods that are supposed to be a lot better. But once we remove this semantic similarity confusion, then that is no longer true. In fact, that raises the question of whether many methods are overfitting to the ground truth, as opposed to actually learning a best semantic space. We're not claiming that to be a fact, but we're questioning that plausibility. Right, so then the second limitation is that it's a big plus. We can use semantic similarity of captions and narrations to improve retrieval, but we really have to rethink our ground truths. Remember that all methods are still using the thing on the left, the assumption that only one caption is correct and the others are not. So we really need to rethink our ground truth. And when we put the paper out, many people visiting the paper told us, but you don't really expect people to change how they evaluate on these standard data sets. I hope that we do, because what we do is incorrect. And someone has to say that, regardless of how the community wishes to proceed. It's actually incorrect to evaluate with the assumption that only one text is considered relevant to a video and vice versa in the current available datasets. Right, so I'm basically telling you lots of potentials for solving problems, but more limitations. And then I'll proceed by some aspects that we've been interested in disentangling the retrieval space, particularly using the sentence parsing or the part of speech. So in this work, fine-grained action retrieval through multiple part of speech embeddings in collaboration with Naver Labs, what we did is we parsed the sentence on the left for its part of speech, i.e. we separated the verbs from the nouns, right? So you parse the sentence and you realize that I put meat on a bowl of dough has the verb put, and then the nouns meat, bowl, and dough. And once we parsed, we then wanted to learn these 2 separate embedding spaces that are disentangled by the part of speech. That means we want a verb embedding space where all putting actions are considered relevant or similar, regardless of the verb of the noun they're applying to. So everything that's putting is similar. And then another space where all the nouns are similar, regardless of the action applied to them, right? So all the balls of dough are close to one another, regardless of whether you are creating them, putting stuff on them, etc. Why did we want to do that? We're actually adding additional supervision into the sentence, but we're also allowing to generalize, because if I know what an open is, then I can hopefully recognize an open for an I haven't seen before. Now, these spaces are not sufficient to do the cross-modal retrieval we're interested in. I still want a sentence in and a video out, etc. But we can build on them. So we can take these 2 embedding spaces. Once we've disentangled these viewpoints or created these multiple viewpoints, we can combine the visuals, combine the text, and have our traditional sentence to video clip retrieval space. So that's possible to do, but we're going via these entangled spaces. You can look at the paper for numbers. I'll just again emphasize the idea that the video is the same. We're just guiding the projection by the parsing of the sentence. That means there is a different projection of the video in the noun embedding space versus the verb embedding space. You can look at the papers for numbers, but more importantly, I want to show you how it really works. So this is one neuron in the part of speech embedding space of nouns and the maximum activation example. So the activations that activate that one first. That means they are actually recognized as common or similar in the space. And we'll start with the noun embedding space, and you'll see examples of a chopping board in various actions in different scenarios being activated by that neuron. So that's similar regardless of the action. And when we flip into the verb embedding space, we see examples of opening or closing being put next to one another regardless of the object. And it's interesting that the neuron decides to put open and close together, so it still cannot separate between them. We also, in addition to parsing by verbs and nouns, we became very much interested in adverbs. And this is a work from CVPR 2020, where again, here we're looking at how to 100 million because narrations in, say, Epic Kitchens are not that long to define adverbs. In how to 100 million, some of the descriptions of certain steps of how to do something will include adverbs because that's the way to actually describe how to do something in a certain way. So you'll find sentences like, you need to dice this finely, or you need to turn the bowl upside down slowly. And one of the missions that Hazel started her work with, and this was also with an internship in Indria, Paris with Ivan Laptev, is to look at whether we can learn slowly or quickly or completely or finely and generalize that to a variety of different actions and objects. Because we know what quickly means, right? We still need to ground it in an action. So the space, the retrieval space we were after, is still a cross-modal retrieval space where, assuming I'm putting these verbs in, we want to take some of the sections of the video that have fining slightly or slicing finely or spreading finely, and we want to put these videos close to the corresponding action, but also make sure that we distinguish slicing finely from slicing coarsely. And it's important to look at the fact that we want this to be general to different actions. That means we want the finely, in this case, we're calling it modifier, to be the same regardless of the verb. And similarly for a variety of different adverbs like quickly or slowly or partially. Right, so how did we do that? And I hinted at this work as one of the approaches to work with single timestamps before, because we also had to deal with the single timestamp notion of a sentence described. We have a timestamp for it, but we don't have exactly the localization of when the action is happening. So we have a video and we have a sentence that says, rolling our lemons quickly or quickly rolling our lemons. We parse the sentence into the action and the adverb. And then we want to embed the video close to not only the action rolling, but a modified version, a transformation in that space, which is based on the adverb. So this is rolling quickly. And as we said, this modifier will be shared, will be learned, and will be shared across different actions. So the embedding space and the modifier are jointly learned. Of course, this would have been ideal if we had clips, but we don't. So to utilize the single timestamps, we know that the action is roughly around the sentence. So we take some video features around the sentence, but then we want to hone on where rolling is happening. And this is where we use a transformer for attention, and the query for that transformer is actually the verb. So the embedding of the verb is the query that allows us to then localize where the rolling is and embed the video of rolling quickly in the space close to the text rolling quickly that is modified by the learned action modifier. So the features are fixed, but the attention, the embedding space, and the modifier are jointly learned. And we have some cool results. So the thick border here, the thicker the border, that means we've localized the action mix, and then we're actually making a decision on the adverb. So once the action is localized, the border is thicker, so this is the attention, and then from that, we're making a decision on the adverb. So we're retrieving amongst the set of different adverbs that we have, and we don't have a long one, I think we have 8, the adverb that corresponds to this one. So you can think of this as an early prototype. It still doesn't deal with all sorts of adverbs. And look at the paper for more details. So this is mixing slowly. And again, you're localizing the action by the thickness of the border and then predicting the adverb. I think one of my favorite examples is this turning example. So I'll just show you that. So this is turning quickly. And again, we're waiting for the turning to know whether it will happen quickly or slowly. And once it's localized, the action, the adverb is predicted. Right. Last but not least, and I think we'll have enough time for questions, is we've talked about the text being a description of the action. We've done some work where we were ranking videos by actually asking for them to be ranked based on the skill displayed in the video. And you'll see the relevance of this work to the previous work. So we want to rank the videos based on certain attributes. And that is, for example, we want the person to be best at the very beginning and the person to be worst at the very end. I say this is still cross-modal because we're querying based on an attribute, but it's not a traditional text-to-video retrieval. And in this work, we had to basically label the videos by their relative skill level of attributes. So you'll have videos like this, and people would look at them and would rank by which, if they believe one is showcasing or demonstrating a higher level of skill than another. And the model to learn this was pairwise, but then at the end, you will get a full ranking when you put a video in testing. So a CME's network that's looking across the video, extracting i3D features. And in the base setup, you would average these features, then have a projection function to learn the ranking and a ranking loss. But of course, not every part of the video is equally relevant to skill. So you want a temporal attention module, similar to what you've seen us doing before, but this is across the whole video. So we have a clip and we want to realize that maybe combing your hair as part of doing a braid is not really relevant, while when you're actually braiding, this is a really relevant part and you want this to be learned. The two CME's architectures share weights. This is now an old work from CPR 2019, but I want to highlight a few things. When we've done that, we realized that, I'm going to skip the disparity loss is purely regularizer. We realized that the network was not really picking what's really distinctive in terms of errors in the action. So it wasn't picking errors as evidences of high attention. And in this work, we actually decided it's best to use multiple attention modules. And up to this moment, they're exactly the same. So they haven't really differed. But we added a rank-aware loss that makes them attend to different things in the video. So one is attending to what's good in the video, and one is attending to errors or what could be used as evidence of low skill. And when we look at the output of these low skill attention modules, high weights here are errors, like someone removing part of the eyeliner or undoing an origami fold. And when we go to the high skill, we realize that this attention module is showing the opposite. So it's firming up or finishing off the pizza rolling. And this was using an older data set, but again, very cool work in my opinion. Right, I had a bit of stuff in explainability in case I have time, and I'm realizing I've taken a lot of your time, so I'm going to skip this into the conclusion. Right, so a reminder, I've presented 4 topics. I hope I haven't overwhelmed you into how you can collect narrations. And then I questioned whether we need the notion of clips and whether we can leverage a larger amount of video text correspondences, similar to how 200 million had done, if we get rid of the notion of a start and end time and we rely on these rough single timestamps. Then I focused on the limitation of the assumption that only one text caption or only one video is relevant to the query, and how this can be leveraged by utilizing the semantic similarity between captions in the gallery or in the retrieval set. We focused on part of speech as one way to disentangle the retrieval space and its potential for actually doing zero shot, but more interestingly, actually doing better semantics, and also maybe other parts of speech like adverbs. And finally, questioning whether we need to retrieve by a sentence or maybe potentially by ranking according to an attribute such as a skill. I get the pleasure of being invited to give talks, but this is work by a large, very active and very dedicated team. As you can see, 2020, we didn't meet, but we met recently in 2021. I'm very grateful for their efforts and focus, and I'm happy to take your questions.
Thank you very much. So we're open to questions now.
Can I have a question?
Yes, please.
Thanks, Professor Dima. Very interesting talk. Just want to take your thoughts about this trend about fine-grained retrieval versus high-level semantics and concept. And so, what's your thought? Do you think that the field and community is going recently towards more fine-grained recognition and retrieval, and they are like kind of leaving out the basic high-level concepts? This is where we are heading.
It's the way we're heading because we can't really assess the high-level ones, right? The explainability of the high-level ones has proven problematic. So we tend to retrieve stuff in the high level and we don't really know whether we've done it right. So part of the explainability approach has taken us down the fine-grained route. That's where we discovered more the limitations, because we now know that we really need to find these fine-grained or detailed aspects. That's how, basically, that's how images had moved a long way by datasets like iNaturalist, or these are the one that discovered limitations of these high level. And I think we're now replicating that phase in video. Note though that not everybody is going down that line, but there's an increased interest in fine grain. I am very interested in fine grain. I think it really hones us into figuring out what is working and what's not.
Okay, great. So one more follow-up on this. So do you agree that we need more tasks and data sets in this fine-grained benchmarking, or do we?
We need to understand the data sets for sure. I think that's the biggest problem. We have enough data sets now. We need to understand what we're doing with them. And then once we understand what we're doing with them, understand what we're missing or what we're lacking. There is a huge number of data sets coming out. So I think looking at the data is really, really critical. What we've discovered with this CVPR paper to me was shocking. As in, when Mike was showing me, I'm like, are you sure? Is this the test set? And we were like going through that and figuring out that, yes, this is the test set. This is how the data sets are being evaluated. I think we need to look at our data sets a little bit more. Maybe they're good enough. Maybe they need better ground truth. Maybe they need, longer descriptions, shorter descriptions, but I don't think we can just use them as is. And at least we need to categorize them to understand what each data set is good for.
Yeah. Maybe even the evaluation methodology need to be adjusted.
Absolutely, the evaluation method. Absolutely, yeah.
Thank you so much.
At least. Thank you.
So we have a question in the chat by Saikiran, and they're asking, what is the intuition behind having a common adverb transformation in the fine-grained retrieval approach?
Yeah. Actually, the motivation came from a similar work of using attributes in images. So the main motivation is to generalize to new actions, is to be able to take a new action you haven't seen, like walking quickly, right? Do you need to learn an example for every combination of verb and adverb? Hopefully not, because you know what quickly is and you can map it even to a new action. Even if I tell you there is an action called, I don't know, BBC, right? It's an action you haven't seen, but this is being done quickly. Can you now look at an example and know whether it's quickly or not? I think you can. So there is a general notion of these things that you can generalize. This is the main motivation, but this is inspired by similar works in attributes where you learn what's red and what's old and what's sporty. and they're using it by unifying the description, in this case, the transformation. I think there were some microphones that were unmuted at some point, so please don't be shy to ask questions. Maybe not, or their questions have already been answered.
So you mentioned that basically when you're moving from video to text, like retrieval, you said that one of the issues is that we're basically saying that there's a single textual description that is the correct answer, whereas it might be
the only correct answer. Yeah,
the only
we're
correct
saying
answer.
it's the only correct answer. Yeah.
Right. So,
Yes,
so do you think like the solution is actually having like basically changing the data set to maybe have by having some mechanical Turkers point out that, okay, these are also relevant to the video, or perhaps like if we use some automatic similarity metrics between these textual descriptions and simply have a soft sort of scoring where you give some extra points for having those in the top maybe 5 or 10 rank. Would that be good enough?
That's our belief, but I think someone needs to do a small scale manual effort to confirm it, right? That's our work, is to move from map to NDCG, where you can actually have this soft scale, and that's a different metric. And then we say that you can use it via some semantic similarity, even though we showcase that one proxy isn't perfect. For example, we have a proxy that doesn't use synsets, so uses just bag of words or part of speech. That means two words describing the same thing. Say a tap for set would be considered different, right? And there's another thing that uses synsets, which is harder to actually correctly relate, right? Because synsets are very ground truth in the meaning of the word. So there are approaches, automatic approaches, that will leverage a lot, and I think we're pushing to say we should use them. But a small scale, we did a small scale manual task, but I would say more needs to be done to understand whether these automatic approaches are sufficient. And I think there is a paper from, there is a paper in ICCV where people showcase that even different language models give you different outputs. It was, I'm trying to remember, because I attended the poster. It was actually looking at different, they were taking different language models, say BERT and GPT, and then they're showcasing that even between these, they would disagree on the description of the sentence, right? So the sentence ends up being slightly different depending on the pre-trained model. So yeah, I think we need to understand more the semantic similarity, and my argument is the shorter the caption, the harder this is. Longer captions are going to give you a little bit more discriminative aspect. Shorter captions will increase the chance of matching, particularly if you have a domain, say kitchen or cooking, or how to do something. This is where that assumption becomes a bigger issue, and yeah, needs to be disclosed, then something needs to happen. Mike will, who's the first author, will tell you, don't do map at all, do NDCG. I think that's an extreme opinion. I would say look at the code that Mike had released, because that allows you to calculate this NDCG. And this might actually highlight some of the potentials in your method by looking at the different evaluation metrics. So we have code out there on 4 datasets that can allow you to do the semantic similarity with, to calculate the your method's performance with the semantic similarity. There's a question.
Yes.
Do you have similar analyses for the audio domain in UCOOC2? The gap between tri-modal retrieval performance seems to be pretty high, with audio probably spoiling the retrieval performance. You mean the audio as in the audio in the video? So UCOOC2, most of the audio tends to be people talking. Yeah, people talking. So I think, well, unbiased, because Epic Kitchens has audio, and that's where we've done most of our audio work, because that doesn't have text. The audio is actually the sound of the actions. And in that case, and again, in a kitchen setting, the audio is amazing, because the sounds of things in kitchen, like the water sound or the cutlery sound or the plate sound, your plate might look madly different, but it will sound exactly the same as you put it down. So for our experience, audio has been really helpful to find those similar videos, which have might have a different semantic context. Audio, when it comes to YouTube videos, sometimes it's relevant, sometimes it's just music, sometimes it's a combination of text and audio. Unfortunately, most of the people who work in audio like audio to be either a music instrument or speech. And we've been kind of trying not to work with these two. So we want to focus on the sound of the action. And of course, there are brilliant works from MIT who've led on this. I'm not claiming for us to be like the only one, but the majority are still speech and like this continuous music, like you see audio separation and it's like a piano or a violin or so. The sounds of actions are really critical. And if you asked me this 5 years ago, I would have said, I am a vision person, I don't do audio. And after collecting Epic and Ego4D, I think we are missing a lot by not doing audio. We have a great opportunity in exploring multiple modalities, and works like Perceiver or other stuff are doing magic in bringing this together. I still don't think we should just put them into this big pot of input, but they're telling us that we should use more modalities.
Thanks. That was pretty insightful.
Thank you for your question. Fantastic. Yeah.
Do we have any more questions?
Don't hesitate to drop me an email or find the first author of these papers who probably knows a lot more than I do, and drop them an email.
Thank you very much. This was a great talk, and I think it gave us a lot to think about as well. Regarding the audio, I remember even with Retrieval, so we had a more general video setting, and in that people claimed that audio was actually detrimental to their results simply because it's very hard to put down what that audio is telling you, whereas in a closed setting, I can actually see it being helpful.
Yes,
so,
especially in an egocentric setting, and you'll see that with Epic and with Ego4D, the camera is traveling to where the action is taking place. So the highest, the loudest action is the sound relevant to the action, right? Which, of course, I'm ego biased, but I think if you're interested in audio, look at the egocentric setup, because the microphone is very close to the action.
Okay, thank you very much. So I think if we don't have any more questions, we will end this session. And so thank you again, Professor Damon. So we have a Gatherly, a social time, I suppose, at Gatherly till 1 p.m. So if you are free, you can just go there, have informal discussions with the participants or the organizers, and I hope to see you guys there. Thank you again for everyone attending, and I'll see you at the social meeting. Thank you.